Friends, welcome to the final session of our second module in RAC. So we have already completed the various type of refrigeration systems, vapor compression refrigeration systems, and we did a lot of problems based on this. And now we'll move to a concept called actual cycle. Actual cycle that is taking place in case of a refrigeration system. So this the type of cycle we have studied in the previous sessions. All those cycles are ideal cycle or theoretical cycle. They are theoretical. Now we are going to learn a concept, the original cycle or actual vapor compression refrigeration cycle. Okay, so the main deviations between theoretical and theoretical and actual cycle. The main deviations or the main difference is that first one, that the vapor refrigerant leaving the evaporator is superheated state. Actually, in the actual cycle, vapor refrigerant leaving the evaporator is in superheated state. So what does it mean? So actually, in our theoretical cycle, you can see that the vapor leaving the evaporator is dry saturated, right? Dry saturated. But in actual case, it will be in superheated. So this is theoretical. This is actual. So the vapor leaving the evaporator will be a bit actually, if it should be in same pressure. So this is a pressure line, so it will be somewhere here. So actual will be little bit superheated. And second case will be the compression of refrigerant is neither isentropic nor polytropic. Okay, so the compression process is not isentropic or polytropic. So in our theory, the compression is like we depict it as some isentropic process, right? S equal to constant, but in actual case, S may not be constant. So compression is not an isentropic process in actual case. Both the compressor, and another point is both the compressor suction and discharge valves are actuated by pressure difference, and the process requires the actual, so it requires actual suction pressure inside the compressor uh, should be it should be slightly below that of evaporator. Okay, so then only there will be a pressure difference, so that compression suction valve operates. So did you understand? So actually, so this is evaporator, so this is compressor. So the actual suction pressure inside the compressor should be slightly below that the evaporator. So this is evaporator pressure. Okay, this is some evaporator pressure, and at the inlet of compressor, the pressure will be same PE. But in order to actuate the compressor valve, the inlet of the compressor should be little bit below the evaporator pressure. Then only the compressor will suck the refrigerant inwards. So that is a major difference. So that is a problem. And another case is that the discharge pressure. Similarly, the discharge pressure should be above above that of condenser, above that of condenser. So students, the discharge pressure of compressor should be, so this is compressor pressure, okay, compressor. So the discharge pressure of compressor should be a little bit above that of compressor, then only the discharge valve will activate. Okay, so there should be a pressure difference between evaporator and compressor inlet. Similarly, condenser and compressor outlet. But in theoretical case, there is no such a pressure difference. The condenser pressure is same as that of the outlet pressure of compressor. Evaporator pressure is same as that of the inlet pressure of compressor. So these are the main differences that we are seeing in the main deviation of actual cycle from theoretical cycle. And another case is that although isentropic compression assumes no transfer of heat between the refrigerant and the cylinder walls, there will be some there will be some heat transfer. Heat transfer. There will be some heat transfer in the cylinder walls. Cylinder walls of compressor. Okay, and similarly the liquid refrigerant before entering the expansion valve is subcooled in the condenser. Okay, and the liquid refrigerant before entering what, entering expansion valve is subcooled. So this may not be the case with theoretical case, but in actual case it is always subcooled in the condenser. Subcooled in the condenser. Subcooled, you know, right? Subcooled means it is cooled below the saturation temperature of condenser. So these, and one more point, the pressure. So okay, these are the main deviations from the main deviations of actual cycle from theoretical cycle. Okay, so the actual cycle almost looks like this. So this is an actual cycle. So it is very much different from a theoretical cycle that we have seen in the previous sessions. So you can see here, so the process here 1 to 2 is nothing but what? 1 to 2, the process shows the flow of refrigerant in the evaporator. Point 1 represent the entry and point 3 exit of refrigerant from evaporator. So 1 to 2 to 3 is completely evaporate, okay, or refrigeration taking place. So the point 1 represents entry and point 2 represents exit of refrigerant from the evaporator, and also the entry of refrigerant into compressor in a superated state. So that is what we have told earlier. In actual cycle, so the up to here this is evaporation. From 3 it will enter compressor. So the refrigerant will enter to compressor in a superated state. Superated state. Entry to compressor. It will be in superated state. That is state 3. Okay. So now, so that is 1 to 2 to 3. Okay. Now we will see that the superating of refrigerant from 2 to 3 is due to. So you can see that 2 to 3 there is a superating, right? Superating means it is heated above the saturation temperature. So what are the reasons for superating? So first one may be the automatic control of expansion valve, so that refrigerant leaves the evaporator as the superheated vapor. And second one will be the picking up of large amount of heat from evaporated through pipes located in the cold space. And another reason is picking up of heat from the suction pipe. So all these may be the reason for superheating in the superheating taking place in the evaporator, right? So okay, now now you can see that from 3 to okay 3 to 4 to 5 6 7 8. Okay, this process is nothing but compression. So you can see that this particular compression is not an isentropic compression or polytropic compression. It is a different kind of compression. So actual compression is neither isentropic nor polytropic. Okay, so this process represents the flow of refrigerant through the compressor. So you can see that at point 3 refrigerant enters the compressor through suction valve. At point 4 the pressure falls due to some kind of resistance to flow during passing through the suction valve. Okay, so 3 to 4 there is a pressure drop due to some resistance while passing through the suction valve. Therefore, the actual suction pressure is less than PE, right? So if suction pressure is PS, it will be less than PE because P4 is less than PE. So this is P4, this is P3. Okay, so then only suction takes place. And at point 5, you can see that point 5. So this is point 5. At point 5, you can see that the temperature is raised due to coming in contact of walls of compressor cylinder. That I've told you earlier that there is heat transfer taking place in the cylinder wall. So temperature is raised. Okay, temperature is raised at point 5. The actual compression is shown by 5 to 6. So this is 5 to 6 compression, and this is due to heat and after that there is a cooling effect in 6 to 7. 6 to 7 you can see a bit kind of cooling, right? So 6 to why that cooling is taking place, this is due to the so that cooling this is taking place at constant pressure, right? Okay, and you can see PC, the discharge pressure PD, the discharge pressure PD will be greater than the condenser pressure PC. So that is P7 will be greater than P8. Correct. So due to the friction resistance of flow through that discharge valve, there is a pressure drop. The actual discharge pressure PD will be greater than the condenser pressure PC. Right. Okay. Now after 8, what is happening? After 8, it should go to the condenser, right? So the process 8 to 9 to 10 to 11 is condensation. So the process represents flow of refrigerant through condenser. So pressure 8 to 9, the process 8 to 9 represents the cooling of superheated vapor refrigerant to dry saturated state. So it is brought back to the dry saturated state. Process 9 to 10. What is 9 to 10? 9 to 10 is a removal of latent heat which changes the dry saturated refrigerant into a liquid refrigerant. So dry saturated to liquid or saturated liquid. And process 10 to 11 is subcooling. So I have told you earlier, subcooling of liquid refrigerant in the condenser is taking place from 10 to 11 before passing it through the expansion valve. Okay. Now 11 to 1. So what is 11 to 1? 11 to 1 is nothing but expansion, right? Expansion. 11 to 1. 11 to 1 represents the expansion of subcooled liquid refrigerant by throttling from the condenser pressure to evaporator pressure. Throttling from condenser pressure to evaporator pressure. This pressure is condenser pressure, and this pressure is evaporator pressure. So PC to PE, an expansion takes place. Okay, PC to PE, an expansion takes place through a expansion wall. So this is the actual. This represents the actual cycle for a vapor compression system. Okay, so this is the actual cycle. All the other cycles we have learned are just theoretical cycle. Okay, now we will learn some factors affecting the performance. Factors affecting the performance of VCRS system, or VCR, vapor compression refrigeration cycle. So students, the first factor is suction pressure. Suction pressure. So what is suction pressure? Suction pressure is the inlet pressure or evaporator pressure. So, evaporator pressure or inlet pressure of compressor. In actual cycle they are a little bit different, but we are going to learn theoretical cycle. So theoretically, if I am drawing the pH diagram, so this is pH diagram. So this will be the suction pressure. Okay, 1, 2, 3, 4. So this pressure is called suction pressure. So this is not actual cycle. We are now learning the effects based on theoretical cycle itself. So this pressure is called suction pressure. So if I am decreasing the suction pressure, say I'm using another color. So this is PS1, and I am decreasing the suction pressure to PS2. So this is PS2, and I am compressing to the same pressure, same condenser pressure or same discharge pressure PD. So this will look like this. Okay, wait. The 1 to 2 process will look like this. Sorry. And it will look like this. Okay, so I am expanding it to the same PD, same discharge pressure, but the suction pressure is a little bit decreased. So what will be the effect? So starting point is this one itself. Okay, so so this is 4 dash. So this is 4. This is 1 dash. This is 1. Okay. So 4 to 1 was the initial evaporation or refrigeration thing. Now this is now it is 4 dash to 1 dash. Okay. So this is the dome. So you can see that 4 to 1 is a bit greater than 4 dash to 1 dash, right? 4 dash to 1 dash. So this amount is a little bit lesser than this amount. Okay, I will draw it once more, for it is not that clear. I will draw it once more. So this is 1. This is this pressure is suction pressure PS1. Okay, and this, okay, I will condense only up to this state. So this is 2 3 4 1. Okay, so this is the condenser pressure PC. I am decreasing the suction pressure to a bit a lower pressure. Okay, so this is PS2. So PS2 is less than PS1. So now this will be the inlet of evaporator. This will be the inlet of compressor. So you can see that the refrigeration effect is little bit reduced, corresponding to the comparing with this, it is little bit reduced, right? Little bit reduced. When suction pressure is reduced, the refrigeration effect is reduced. And now if you compress it to the same pressure, it will look like this. So this is 2 dash. Okay, so same pressure means it will be somewhat towards the right of 2. So students, the conclusion is that first one, refrigeration effect is decreased. If suction pressure is decreased, refrigeration effect is decreased. Second one, work of compressor is increased, right? Because you can see here, this value is a little bit lesser than this value. Okay, so work of compressor is increased. So COP is RE by W, right? So RE is decreased, work is increased. So COP is decrease. Okay, so effect of suction pressure is a decrease in COP. So it is not desirable. Now the second, we will learn about effect of discharge pressure. Discharge pressure. So discharge pressure you can see here. So this is 1, 2, 3, 4, 1. So if I am, so this is a discharge pressure PD1. Okay. So if I increase the discharge pressure, increase, so let me increase the discharge pressure to some PD2. Okay, PD2 is greater than PD1. This is PD2. So 1 to 2 dash will be, so this will be the 2 dash. And this will be the 3 dash. And this will be the 4 dash. Okay, the cycle changes like this. Okay, so you can see the result will be, you can see that there is a decrease in the refrigeration effect, right? So the refrigeration effect 4 to 1 is less, 4 dash to 1 dash is now 4 dash to 1 is less than 4 to 1, right? So there's a decrease. So this is, you can see here. So this is less than this value. So this value is greater than this value. So there is a decrease in refrigeration effect and increase in work required. So work required is increased this much. So that too is not desirable. So COP is decreased because refrigeration effect is decreased, work is increased. So COP decreases. So discharge pressure increased means it is undesirable because here COP will decrease. So that is one point, and the third parameter we will learn about superheating. Okay, superheating. Superheating. Now I will draw the superheating case here. So this is 1. Okay, this is 2. This is 3. 4. This is 1, 2, 3, 4. This is a cycle. Now, if I am superheating this, superheating the vapor, okay. I'm superheating the vapor means to increase the refrigeration effect. I am superheating from 2 to 2 dash. I am superheating at constant pressure. So the what will happen? The refrigeration effect is increased because 1 to 2 is less than 1 to 2 dash. So refrigeration effect is increased. So new refrigeration is 1 to 2 dash. So it is increased. Okay. So if it is increased means, so the compression will be like this 3 dash. So this is the same pressure. Okay. So 3 dash to 4, 4 to 1. Here you can see that refrigeration effect is increased, but there is an increase in work, right? So the effect of superheating is to increase the refrigerating effect, but the increase in refrigerating effect is at the cost of increase in amount of work. So this 2 dash to 3 dash will be little bit greater than 2 to 3. Okay. So here you can see that COP is RE by W, right? Here RE is little bit increased, W is also increased. So COP cannot be assumed that COP increase or decrease depending upon the correct amount. It is not sure. Okay, so the increase in work is more. If the increase in work is more as compared to the increase in refracting effect, there may the COP may decrease. But if the increase in refracting effect is more compared to W, COP may increase. So it is not predictable. It depends upon the situation. Okay, so you understand. You try to understand that even though refracting effect is increased, the work required in compressor also increases. So that is the problem. And now we will, fourth one is undercooling or subcooling or undercooling. Subcooling or undercooling. So we have done the problem based on subcooling. So here I will show you a figure. So this is our pH diagram. So here, suppose this is 1, 2, 3, 4. So undercooling means a little bit cooled below the saturation temperature. So this is 3 dash. Okay, from 3 dash to this pressure. If this is 3 dash, this is cooled to 4 dash. Okay. So now here in case of undercooling, the refrigeration effect is 4 dash to 1, right? So before undercooling, with undercooling, refrigeration effect is increase, right? Refrigeration effect is R is increase in case of undercooling. So no change in work. Work is same. Work is same. So what happened to COP? COP will increase, right? COP increases because if work is constant at the same time refrigeration effect is increased means COP is increased because COP is refrigeration effect by work. So the subcooling, the effect of subcooling is to increase the refrigeration effect, and along with COP, along with there will be an increase in COP. Provided that no further energy has to be spent on obtaining extra cold coolant required. That is a point. Don't worry about it. So there are four. We have learned four factors. First one, suction pressure. Suction pressure. So suction pressure decreased means COP is decreased. Discharge pressure. Discharge pressure increased means COP is decreased. Third one, superheating of vapor coming out of evaporator. Superheating of vapor coming out of evaporator means if it is superheated, it won't have that much impact on COP. And fourth one is undercooling or subcooling. Undercooling will increase the COP definitely. So these are the four different factors affecting the working of a theoretical cycle. So these parameters are important. Okay. Now one more point we will learn a concept called a liquid suction heat exchanger. Liquid suction heat exchanger. LSHX. So this is liquid suction heat exchanger. So what is a liquid suction heat exchanger? So students, liquid suction heat exchanger is a counterflow heat exchanger. Counterflow, a type of heat exchanger. Counterflow. So you have learned different types of heat exchanger in HMT class, right? Counterflow, parallel flow, closed flow. So this is a counterflow heat exchanger in which the warm saturated refrigerant liquid from the condenser exchanges heat with a relatively cool refrigerant vapor in the evaporator. So what is that? It is a so here you can see heat the liquid. This is LSHX. Okay. So this is placed in between condenser and expansion. So this is compressor in evaporator. So actually from evaporator the vapor should go to compressor, but here there is a heat exchanger in between that. So the heat exchanging takes place between the vapor flowing through evaporator to compressor and the liquid flowing through, sorry, the warmer liquid flowing from condenser to expansion valve. So here heat exchange takes place. So heat is actually added to this side. So because the warmer liquid from condenser will reject heat to the cooler vapor that is flowing from evaporator. So the liquid suction heat exchanger is a counterflow heat exchanger in which the warm saturated, so you can see, we will say once more. So this is a particular heat exchanger in which the warm saturated refrigerant liquid coming from condenser, so this condenser coming from condenser exchanges heat with relatively cool refrigerant vapor from the evaporator. So from the evaporator, a cool refrigerant vapor is coming. So it will absorb heat from the warm refrigerant, liquid refrigerant coming from condenser. So here to here there will be a heat exchange. So in cooling the liquid and reducing its enthalpy, a greater refrigerating effect will be obtained. So here we are cooling this. This warm liquid is cool because it rejects heat. So in cooling this liquid, and its enthalpy is a little bit reduced. So a greater refrigerating effect is, so cooling the liquid coming from condenser will yield a better refrigerating effect. So we can see this using a figure. So students, you can see here. So this is TS diagram. This is pH diagram. So actually there is a I'm trying to zoom this. Okay. So actually here the heat transfer, so the liquid heat exchanger works between this condense. It is actually transferring heat from 3 to this evaporator, the condenser to evaporator, right? So due to that transfer of heat, the liquid gets cooled from 3 to 4. 3 to 4 cooling takes place, and the evaporator, and this is at evaporator what happens, heating takes place from 6 to 1. So actually it should be at 6, now it is heated to 1. So a kind of undercooling takes place. Undercooling takes place. So undercooling definitely increases the COP, right? Undercooling definitely increases COP, that we have learned. So placing a liquid suction heat exchanger means it increases COP, right? Right. So you can see here now. If liquid heat exchanger has not been placed, means from 3 to 4 it will be like this. So this will be 4, and the process will be like this. So refrigerating effect will be this much only. So since liquid heat exchanger is placed, the refrigerating effect is this much. Okay, this much refrigerating effect. So refrigerating effect is increased definitely. So it means COP is increased, but the work in compressor is not that much increased. It is almost same. So refrigeration effect is increased with with placing liquid suction heat exchanger in the path of condenser, warm liquid from the condenser to expansion valve. So that is the advantage of using a liquid suction heat exchanger. So with this we will conclude the this module. Okay, thank you.